Hey everybody, we're starting out Unit 8 with a look at our chi-squared goodness of fit, and we're going to introduce this concept with some M&Ms. So if you haven't already, go ahead and grab one bag of the M&Ms for your group of 3, and go ahead and sort them by color and count how many of each color you have. And we're going to collect all this data on the board, and if you'll pause the video here, do that, and then we'll talk about what we're going to do with that data. All right, so hopefully you have your numbers, and the values that you got as a class should be listed right here, okay? So total up all the browns that the entire class got, all the yellows, all the oranges, all the greens, all the blues, all the reds, and the total number of M&Ms that you guys counted. And that's the data that we're going to work with here. Those are known as our observed values. Okay, that observed idea is going to come in handy here in a minute because that's part of our formula. So what are we actually doing with this? Well, we just found the number in our total sample, this giant bag that we started with, of each kind or each color of M&M. And according to Mars, so who makes M&Ms, they fill each bag with about 13% brown, 14% yellow, 20% orange, 16% green, 24% blue, and 13% red. And we could analyze individual colors here using, say, a proportion test or something like that. But what we want to do is we don't want to just look at one color. What we want to look at is this entire claimed distribution, okay? This is our claimed distribution. This is what the company says happens. And what we want to see is if there's enough evidence from our sample to determine that this is not accurate or to confirm that it does seem to be accurate. All right, so let's talk about how we're going to approach this, and I'll have you guys pause again here in a little bit to do different steps of this. But first of all, as with any test, we want to determine what the hypotheses are for this significance test. And we're talking about a goodness of fit. In other words, do our data actually fit this distribution they're claiming exists? So we're going to assume that they're telling the truth, first of all. So our H sub naught is that the claimed distribution is accurate. The claimed distribution of colors is accurate. And then, of course, our alternate would just be that the claimed distribution of colors is not accurate. Okay, the claimed distribution of colors is not accurate. Now, notice this is not going to tell us necessarily if it's not accurate. It's not going to tell us like which color is off or which colors are off. We'd have to do some more analysis for that. But this is what we'll do here. In the goodness of fit test is we're just going to say, is the distribution overall accurate or not accurate? So what we need to do first of all is we need to determine expected values. In other words, assuming H sub naught, assuming the percentages given above, how many of each type of M&M would we expect? Now, I'm going to make up some numbers up top just so that we have something to work with here. Let's say that we've got a total of 300 M&Ms, and out of these 1, 2, 3, 4, 5, 6 different colors. Let's say we had 40 and 60 and 50 and 45 and 55 and 50. I think it should add up to 300. Yeah, 100, 100, 100. Yep, that's 300. So our expectation out of 300, if we have 13% brown, we would do 13% of that 300. We would expect to get about 39 brown, and that looks about right so far. But then we do the yellow. If we have 14% yellow, 14% of that 300, we would expect to be 42 yellows. And you can see, whoa, we got actually quite a few more yellows in our sample, okay, or at least in my made up sample. And you do that for each one of these. I'm just going to stop there so we can see the idea. So now we're going to construct what we call a chi-squared statistic, okay? A chi-squared statistic, if we look at table C in our formula booklet, okay, we see a chi-squared critical values, okay, right here. That letter chi is a Greek letter there, but this is a chi-squared distribution. You can see that this is a skewed distribution. This is not a approximately normal or normal distribution. And the reason is because in our calculations, as you'll see, all of our values are going to end up positive. And we're talking about distances away from that claim, okay? So we would expect more of the distances to be closer to zero. And as we get further and further away, the likelihood of getting something further and further away from the claim is going to be less and less. And that's why this is skewed to the right, because those probabilities of being really high up here are less and less. As you'll look at the formula is up here on the first page. You can see our chi-squared statistic is the sum of, that's what this sigma here stands for, the sum of the observed values minus the expected value squared over the expected value. So we have this ratio, and notice when we square it, it's always going to end up positive. That's again why it's skewed and close to zero. Let's look at actually doing that with just like our brown and our yellow. Okay, so what I would do here is I would take the observed up here was 40 and 60 for the brown and the yellow. The expected we're getting from these ratios where we're assuming that the claim is true. So assuming the claim is true, we should get 39 brown and we should get 42 yellow. So what this table allows us to do is just kind of build our parts of the chi-squared statistic. So 40 minus 39 is 1. 1 squared is 1. And then we're going to take that value there and put it over the expected. So 1/39 is what we've got there. 1 out of 39 is about 0.0256. I wouldn't round too much. Because you're going to use, we need to add all these up. That's what that sigma said, was to add all these up once we've calculated. So I'm going to keep that as a 0.0256. So now I have part of it. I do the same thing for yellow. 60 minus 42 is 18. 18 squared is 324. So I have 324 over that expected number of 42. And when I figure that out, 324 out of 42 would be 7.7143 if I go same number of decimals. So 7.7143, and so on. We continue this process, and notice the last thing here it says to do is add up all the numbers in the last column. So when we get all these values and we add these up, that sum is going to go right here, and that is our test statistic. The chi-squared equals whatever that total is. All right, so now we have to come to a conclusion. All right. As we saw in that distribution I showed you, the distribution of the chi-squared statistic. Scroll all the way down, look at our last page at that chi-squared distribution. The higher the value, the lower the probability is. Okay, so in other words, if our true distribution fits the claim, we would expect the differences to be relatively small. We would expect the chi-squared to be relatively small, and therefore we would then fail to reject the H sub naught. We would say, okay, yeah, it seems to fit. But if we're getting a very large chi-squared value, we would say that, okay, that seems to be some evidence that our claim is not true. So let's see how we would use this table in order to make that determination. Well, if I come down here, you can kind of listen to what I would just said to figure out number 4. But let's make a conclusion based on this information. And let's just say, for argument's sake, let's say that our chi-squared came out to be somewhere like 11.3. Okay, I don't know what it would be with what I gave you, but let's say it's 11.3. One thing that we have to consider is our degrees of freedom. Now, degrees of freedom here, it's kind of similar to what we did before. We are going to subtract 1, but we're going to use k minus 1. Notice our n in this case was 300. That's not really significant when we're talking about degrees of freedom. Degrees of freedom, we're actually concerned more with how many categories we're dealing with. In this case, there were 6 different colors. So the idea here is that if I knew any 5 of those, like how many were in each 5, the last one would automatically have to be the rest of them. So the degrees of freedom is my total number of categories, 6, minus 1. These are the 5 that can basically be anything, and then that 6th one just ends up being whatever the rest are. So that's that degrees of freedom idea. So I've got a chi-squared of 11.3, degrees of freedom 5, and I come to my table C, and I'm looking at this row where the 5 degrees of freedom are. So I'm looking right there, and I look for my value. Now I had chosen 11.3, just out of the air here. So 11.3 would fall right here, okay? Now, because 11.3 is between the 11.07 and the 12.83, it's going to be, our p-value is somewhere between 0.025 and 0.05. And because we want to be a little more conservative, we're always going to defer to the higher p-value. So we're going to use a 0.05 for this p-value, okay? So from table C, the p-value is about a 0.05. Now you might say, ooh, 0.05, that's kind of like our alpha. If our alpha was a 0.05, how would we deal with that? Well, this is where we could actually think about what we really know. We know it's not actually exactly 0.05. We know it's between 0.05 and 0.025. So we could actually go ahead and reject H sub naught in this case, at least with my made up data, because our p-value we know is actually less than 0.05 and bigger than 0.025 in that range. Now we'll look at using our calculator to get an exact p-value later, but for today what I want you to do is go ahead and finish this simulation, find a chi-squared, and see if you can find an approximate p-value for our data. Okay, so have fun and have a snack when you're done.